Okay, well, we'll go ahead and get started. Welcome everybody that's on. We appreciate your time. Welcome to another IGSHPA Town Hall segment. We've got the pleasure of Mike Burton joining us today to talk about a hospital project that he worked on, and should be very interesting. Got a little bit of housekeeping here just to start, and then we'll turn it over to Mike. News and updates, a few things that we've got going on. Obviously, we're continuing our town halls and dig deeper webinars. So if you're interested in any of those, make sure you check out the IGSHPA website and look at the list that's coming up. There's a lot of good ones that are on the docket, and hope to see you there. So we appreciate you attending. And then, of course, if you're looking for that, just go to igshpa.org and go to the events tab, and you should find a whole menu of registration links that are now available for the upcoming town halls and dig deeper events. So the 2022 annual conference has been basically booked, and we're partnering again with the National Groundwater Association. This next year it'll be in Vegas in December, and so the planning is happening on that, and we're really excited. So we're hoping to see you all there in Vegas in December. And more information will be coming on the website, obviously, as we get further down the road with planning and setting the schedule, et cetera. CEUs and renewals. We're no longer waiving CEUs for 2022 renewals. So just keep that in mind if you're renewing any accreditations or certifications. And the town halls and dig deeper events and the annual conference now qualify for CEUs, so make sure you keep track of that. And it's very important that if you'd like CEUs for this town hall, send us a chat message while on the Zoom meeting, and we'll record that, and we'll make sure we get you the CEUs for that. Again, throughout the presentation, we'd appreciate it if you put yourself on mute and hold your questions till the end. We'll have a Q&A at the end. And of course, if you're thinking of something, just use the chat feature in the Zoom function that you can ask a question, and then we'll get to those at the end of the presentation. Okay. Again, please mute your microphone unless you're talking. So, and we are welcoming in Mike Burton. Mike is a PE. He earned his bachelor's in mechanical engineering from Tennessee Technical University and has 34 years of experience. He's been with Smith, Seckman, Reid for 20 years. He's a senior mechanical engineer, and his expertise is a wide range of design, including central energy plants, HVAC systems for healthcare, institutional, and commercial facilities. And he's also a member of the Nashville, Tennessee ITERATIVE chapter, and he's registered PE in 16 states. So we're very excited to have Mike. And with that, I will turn it over to Mike.
All right. Can let me share my screen. Okay, can everybody see that okay? Can everybody hear me okay?
We can hear you, Mike, but we can't see anything. There we go. There it is.
Is that it?
Yep, perfect.
Great.
Thank you.
Perfect. Very good. Well, I am glad to be with y'all today. Thank you, Brian. Thank you, Jeff and IGSHPA, for the opportunity to share with y'all today. We're going to be talking about a specific project that I was involved in the design, and we have a long track record of operations, and it's Methodist Olive Branch Hospital in Olive Branch, Mississippi. And basically just want to walk through this story with you. It's an exciting story. We like to tell it. It's one that it was a challenge from the very beginning, but we are very thankful for the results that we see, not only right after or not too long after the hospital opened up, but even as it continues to operate today. So it is, oftentimes with design and construction, you hear about, the project when it's done at the end of construction at the ribbon cutting, but you don't hear much about it afterwards. And that's one of the unique things about this, is we've been able to tell the stories and provide some results after the project was actually done and completed. So there we go. As Brian said, I've been with SSR 20 years now. We're very thankful to have worked here. It's been a great experience, and this has been one of the projects that I enjoy working on. As I said, it was a challenge, but it was fun to work on with and not only us as a firm, but we partnered with Turner Construction, and Gresham Smith was the architect on the project. I think even Steve Hamster, maybe on the town hall today, was involved through a company called Greensleeves back at the time, that we actually used some of their technology that I'll go into a little bit later. But anyway, it was a team effort, and I'm glad to be able to share it with you today. So one of the things we'll be talking about today is, and this is a ground source heat pump project, but one of the things I want to run through with you is a little bit about the project. Understand the approach to the design selection process, because that's a key in a geothermal heat pump project. Oftentimes, we get, how do you ever get to the point where a ground source heat pump project gets incorporated in the design, especially on a hospital? This is a 225,000 square foot hospital. So how does that happen? So I want to kind of walk through that, understand the importance of, the performance parameters during the selection process. And obviously most everybody here on this call is, has experience or been exposed to ground source heat pumps, but for many it's a new concept. But I would say probably for most, maybe in a hospital setting, this is a unique application. So I want to kind of talk about the implications of that. And then one of the keys that often gets left off on a project, but it's understanding the impact to the operation and maintenance staff. And so that's a real key in this, is we've gotten a lot of feedback from the facility on this project, and has some great information to be able to share in that realm as well. So, but kind of our roadmap, this is going to be about 45 minutes. We should have time for questions at the end, but as I said, give you a project introduction, kind of the selection process, overall system description, and then we're really going to dive into some of the performance results that are available, and not just right after opening, but even up until 2021. We don't have 2022 data yet, but we do have 2021, and then, like I say, we'll have some time at the end for questions. So this project is located in DeSoto County, Mississippi. It's right over the state line from Memphis, and it really kind of has an interesting story. Methodist Olive Branch actually is based in Memphis, but they actually started the CON process in the 90s to try to get a hospital built in this area. It actually took 18 years for the CON process to go through. So there was a lot of politics, a lot of timing that was going on. And so basically what happened is, because of this history of the project, it actually set the stage for a speed to market approach, which is a real key when you think about a unique, HVAC system, and combining that with a speed to market approach. And it was a very, very aggressive schedule, which I'll kind of walk through here in a minute. But at that particular time, if you remember, in the 2010, right after the 2008 financial crisis, so there's a lot of upheaval in a lot of different areas, but obviously one of the things that we still want to maintain in a healthcare setting is patient satisfaction. But there was all kinds of things going on with reimbursement cuts, staff retention, all of these factors that were a big drive to reduce costs, to improve patient satisfaction and reimbursements. And obviously with any project, you have the old adage of, on time and budget and quality. You can't have all three, but everybody wants all three. And we feel like we were really able to achieve that on this. But as Clay Seckman says, one of the guys here, the son of one of the founders of our firm, he says, so in the midst of all this, all these competing, criteria, is kind of like trying to eat Oreos and brush your teeth at the same time. There's a lot going on, in other words. So a lot of challenges that were very clear, very prominent but it was exciting to be able to engage them all. So real quick background on the project, it's 100 beds. And basically the owner came to the design and construction team and said, we want 100 beds for $100 million. That was the criteria. From selection, in other words, from when the design construction team were selected, and I'll go into this further, but this was an integrated project delivery where the design team, the construction team, subcontractors came on early to speed the design and construction process, but the owner's goal was to go from selection to occupancy in 24 months. And if you know anything about, healthcare design and construction, that's a very aggressive schedule. Normally a project like this would take about 4 to 5 years from inception of design until occupancy. So very aggressive schedule. Wanted an efficient hospital, wanted an Energy Star and LEED Gold facility. So you put all that together, that was a high mark. So kind of like this old Far Side cartoon, if we can pull this off, we'll eat like kings. So it's kind of a little bit the way it felt. But like I said, one of the keys in this whole process was not to ignore or reduce in any way patient safety, satisfaction, staff retention. That was a big driver. Having high satisfaction, a community approach to the project. So a lot of what this drove with all of this, it was a non-linear, non-traditional design process. We also looked in the process of looking at this, we looked at O&M, operation and maintenance, what kind of intrusion into the facility. We actually went and looked at a heat pump project in Louisville, Kentucky as kind of a comparison before we went down this road. Noise or lack of was a big factor. So anyway, I say all this to say that this was a tall bill to fill. And so in order to do that, this project took a integrated project delivery approach. The traditional delivery, which you can kind of see on the top is the design team is represented kind of there in the blue. There's minimal involvement with the construction team on the very beginning. And then once you kind of get toward construction, there's a little bit of crossover. And then, toward the tail end of the project is more construction, less design. But the integrated project delivery is get everybody involved early, all the way through to the end of the project. And so that's the way this was approached. And the reason for this kind of gives a graphic example of why to take this approach, and we'll talk about why it worked so well on a geothermal heat pump project. But in a typical traditional project approach, there's a lot of time spent, really on the construction documents. There is some design development. There's kind of minimal time spent on the schematic. But I just lost my slide here for some reason. But with the integrated project delivery approach, there's actually more time spent on the schematic front end with a lot of iterations of design. And so that's the approach that this project took. So obviously with any project, but particularly for a hospital project, the HVAC system selection is and what it is and how it's the impacts of that system to the overall project and facility. There's a lot of things that impact the HVAC. The thing that I guess most everybody's familiar with, and you often hear this with particularly ground source heat pump with the geothermal field is first cost. How do you avoid having first cost drive everything? And so when we took the approach in selecting this HVAC system, we tried to take into account all the things that you kind of see represented there in the slide, from first cost to space requirements. I've already mentioned the patient satisfaction, energy costs, obviously, electrical impacts to the system, selection of, the window and the glazing for the project. So a lot of different factors, but the whole key was to stay in budget. And so one of the things we did on this, we used component teams, to where each component team, like the HVAC was a component team, and there was a structural team, and there was an envelope team, and all these teams had a certain budget they had to stay in. And if they found that they could give up money on one side, they could take that money and transfer it to another team, another bucket. but overall, that goal of $100 million was what we were required to say in as a team. And to give you an example of kind of this, I remember very vividly being on a call with kind of the HVAC component team, and it came up a lot of the equipment that we'll get into in a minute for the DOAS units, for the dedicated outside air system for rooftop units. And so we had to do, so originally there was a lot of screening, but there was some of the units from the backside of the hospital, and the owner was on the call, and he kind of said, well, hey, these units on the back, if we don't have to screen them because they're in the back and nobody can see them, and if the local code authority doesn't require them, do we have to do that? And he just kind of, because we were going to, and he just kind of asked the question, well, come to find out, no, the local AHJ didn't require it. So with that one conversation, we knocked out $1 million of screening, in that process. So that's just kind of an example of how the component teams worked. But to get this project started, I very vividly remember this. In July of 2010, we had a blue sky session back in our conference room in our office, and we had the architect, the contractor, full design team, everybody, and the goal was to have a blue sky session to throw up ideas about this project and how we could do it, and possibly how we could do it differently. It was never from the beginning, oh, hey, we're going to do ground source, heat pumps on this project. That was just happened to be one of the things that was mentioned in this blue sky session. But it's a key because there were no bad ideas. There was not anything nobody was allowed to say, hey, we can't do that because of this. That blue sky session was put ideas on the table. We'll come back and evaluate them later. And so that's how really the ground source heat pump system even got started and considered on this project, was from this blue sky session. There we go. My advancer is slow, it looks like. So in this process, it was very iterative, and this goes back to what I was talking about, spending more time in that schematic design. It was, we wrote multiple narratives on this project with multiple different systems. The contractor would take it and price it. They would come back. We would make revisions on that schematic design. So we went through a very iterative process. We would write something and price, get the results back, discuss it with the owner, and we went kind of round and round multiple times looking at different systems. So in this iterative process, we looked basically at 5 systems. We looked at a traditional chiller, boiler, VAV air handlers. We looked at water source heat pumps, being heat pumps that would be provided water instead of from a ground source. Geothermal field, it would be a cooling tower and boilers. We looked at variable refrigerant flow systems, active chill beams, and then ground source heat pump, as I've already mentioned. But the graphic here of the comparison of the heat transfer capability of air, water, and refrigerant. This is a big deal in hospitals because obviously if you look at air, in order, that's 0.48 BTU hour, per pound. It takes a lot larger duct to transfer a certain amount of heat than it does with water and refrigerant. So obviously the further you move to the right, the less space gets taken up in the hospital. And space in a hospital, and at that time it was about $300 a square foot. It's more than that now. But at that time, that's a lot of money when you talk about, taking up space. So that was one of the goals, is to be able to reduce the space. And then the other was to be able to decouple the dehumidification from the space cooling. And we did that with dedicated outside air system units, as I've already mentioned. And one of the big keys, particularly for a hospital, was to be able to reduce the simultaneous, cooling and reheating that is often a big, energy consumer, especially for a hospital. So as I said, we looked at chill beams, we looked at geothermal, we looked at multiple different system types in order to achieve the goal of trying to reduce this reheat, which in a hospital is often over 40% of the energy costs of a hospital. So if you can knock out part of that reheat, you do a significant, it's a significant way to reduce the overall, energy consumption of a facility. So that was one of our goals in being able to do that. So what we did, this is early on in the project, some of you have probably seen these. They get used a lot on projects now, but this is an A3. It's basically a way to summarize a decision process on a project. So this is the A3 that was used to evaluate the HVAC system. And so we'll kind of walk through this. I know you probably can't see all of it in detail the way with the size of the slide, but we'll kind of walk through each particular part of this to walk you through the selection process and show you how we ended up at a ground source heat pump. And the first thing that always gets, you know, the most time and attention, I guess, on a project in selecting a system, it's the first cost evaluation. What is the equipment cost and what's the electrical cost? Those are kind of the things that probably pop up the most. But one of the things that we looked at in this, as I mentioned back to that slide about the air versus water and refrigerant, the amount of space it takes up, is you know, floor space. If you can reduce floor space, you can, you know, obviously save square footage. The other one that often gets ignored is floor to floor height. If you can reduce that floor to floor height, you're able to reduce the overall, you know, cost of the project. So the ground source heat pump reduced the overall building height by about 4.5 feet, and the reduced MEP space, and I'll go into this a little bit more in detail, but we really did not have any large mechanical rooms. They were all equipment closets for heat pumps. And then if the large, you know, DOAS units were on the roof, so we did not have any large MEP spaces. We didn't have a boiler room, we didn't have a central plant. So we were able to reduce the MEP space by about 5,400 square feet, and at $300 a square foot, that's like $1.6 million in savings. So that's the way we were able to look at, say, maybe a more expensive HVAC system that had a large upfront cost, say, with the bore field. It was looking at the overall first cost of the project, not just the equipment cost and not just the HVAC cost. The second thing is just energy versus operation and maintenance. To look at the total life cycle cost, you know, of the systems for each one, and then comparing the operation and maintenance, and that includes, you know, how much staff would be required. And one thing, like with a hospital, so if you have a steam boiler, most states would require a 24/7 operator to be on to be at the facility. So that means if you don't have, you know, a steam boiler, you don't have to have somebody there 24/7 as a boiler operator. So all of those things were taken into account, you know, both on the energy side and the operation and maintenance side, in order to fully evaluate the total cost of each HVAC system. So here's kind of what it looked like. So all those factors I just mentioned, again, got rolled into, this is actually a clip from the A3, but we rolled all those costs in on each of those systems, and here's kind of the way it came out. And as you can see, the ground source heat pump was not the absolute lowest on the energy cost on the first one. But in comparison between ground source heat pump, water source heat pump, at least on this, they were close and a lot lower than obviously the other three, you know, by comparison. So yeah, and that's the first cost. But when you get to the energy costs, the ground source heat pump obviously came in a lot lower, and so that was the huge advantage of the ground source heat pump, was the annual energy cost. And in this particular, you know, a lot of times on projects, owners are not willing to look at the say a long-term or at least even a short-term life cycle cost analysis, you know, and what they'll say with energy, because they're looking at the bottom line budget on the first cost of what the equipment is. But this particular owner they had an overall, as I said, an overall $100 million budget goal. As long as we stayed under that on the first cost, and in particular, if we could show a return on investment on part of that maybe larger expense on the HVAC side than normal, they were willing to entertain that. So the O&M costs, again, the ground source heat pump came out less. And a lot of times we get the question about the water source heat pump, what made that more? Well, one, you've got cooling towers, there's water treatment, there's water usage, there's water evaporation. All of those kind of go into that elevated cost compared to the ground source heat pump. So here's kind of a summary of where it came out. We looked at the EUI for each of the systems, the annual energy cost per square foot, and the first cost. And initially, we compared it over a 7-year period. The owner actually, and that's kind of what the initial basis of design was that we were looking at. The owner actually came back later and said, "Hey, can you make it, pay back for 5 years?" So it was close, but we were able to show that it would pay back, in a 5-year period. So basically, to summarize, the ground source heat pump versus the water source heat pump, there's like a $450,000 savings over the 7-year period. And between the ground source heat pump and the VRF, there's like 1.5 million, and then the ground source heat pump versus a chiller VAV system is like 2.3. Again, that's total cost of across all of these over a 7-year period of time. So obviously, the ground source heat pump was the best system from that evaluation. So what did we end up with? What did it look like? Well, we had distributed ground source heat pumps throughout the facility. We had rooftop DX DOAS units, and we actually used natural gas for the preheat on those. We had water-to-water ground source heat pump for domestic hot water. And as I mentioned and alluded to earlier, we had no central steam, no blowers at all. So you might ask, well, so what about sterilization for central sterile? Well, what they did is they provide, and you can with sterilizers and central sterile equipment, you can get onboard steam generators, and that's the way they approached it, is those onboard steam generators were provided with the equipment. But we did end up with 196 vertical bores at 300 feet deep. And then one of the unique things about this site, this is about a 60-acre site that, as I said, is an olive branch just south of the Tennessee state line, right outside of Memphis. But one of the things on this site was there were some wetlands and a blue stream issue that did not allow the use of the whole site. And so we were limited on what the bore field size could actually be. And so this is where we actually did, this is where the green sleeves package pump system and adaptive control came into play, because we did have an 80-ton fluid cooler that could be operated both in the wet and the dry mode. And the reason for that is, so in this adaptive control, it's basically anytime there is the opportunity to kind of pre-cool or recharge the bore field, by this adaptive software, it picked the right time to do that and would divert flow, either if there was actually during a peak time, if it needed the fluid cooler, it would do it, or it would pre-cool when it was during off times, and it was advantageous from an energy perspective to be able to do it. So this was one of the ways that we were able to serve this entire facility with a smaller bore field that was restricted because of the site limitations. And the fact, like I said, that the DOAS units are not on the bore field, it's only the ground source heat pumps. So, but that's kind of a schematic and overall view of how we did the building systems. So when you start looking at patient rooms, so what did the patient rooms look like? Well, each room had its own heat pump, and this is kind of an isometric view with if you see where the blue arrow is, that's where the closet, and we'll look at that here in a minute, but that's where the closet for the heat pump was located. And the ductwork would come out of that room and serve that, that patient room. And then the water from the geothermal wells, was piped in, to each heat pump, distributed throughout the building. Here's another representation of it. And again, these are the patient rooms, and we were able to do closets where we could do 2, heat pumps in one closet that would serve 2 different rooms. And that graphic on the right is kind of the isometric of what that looked like. But that's kind of how we laid out the whole system. And then when you look at it from a floor plan perspective, all of the dots, the red dots that you see represented, those are actually the locations of the closets. And then the picture on the lower right, they were basically louver door type closets. And the way that we were able to do the heat pumps was the maintenance was all front access. So basically the doors of those closets could be open and the heat pumps could be serviced from the front, so that it allowed us to minimize the size of that closet and still provide maintenance access. And then as far as how we handled the outside air, there were, like I said, DOAS units, dedicated outside air systems on the roof. So in this slide, that blue rectangle, which was located on the roof, provided the outside air, which is in red, to be used, provided to the heat pumps throughout the facility. In this particular graphic, the green is where the heat pump is located, so that outside air comes into the return of the heat pump, and that's how we provided outside air to each of the ground source heat pumps through the facility. This is a particular shot of one of the DOAS units being installed, and then the picture on the right is actually of the green sleeves pump skid that was installed, that was used in conjunction with the fluid cooler. So, and then again, another picture there on the right of another heat pump closet. It was not a patient room, but it would have been another closet, another heat pump closet in the facility. And as I said, I'm not going to spend a lot of time on this, but we did use DOAS units, energy recovery, because obviously by doing that, you reduce the overall load of the outside air. So we were able to significantly reduce the tonnage of the DX units that provided the preconditioned outside air to the heat pumps. So what were the performance results? And this is what everybody's always interested in. So this just kind of gives we'll just kind of run through several slides here that kind of give an overview. That graphic up at the top is from the A3. And we had estimated when we did that 7-year evaluation timeline that the energy cost over 7 years would be a little over $5 million. So that's $722,000 a year. The first year of operation. So kind of give you a timeline here. So the design team was selected in 2010. We basically had about a year to construct it. And then the construction team had about a year to build it. And so it was completed and occupied in August of 2013. And so these performance results are 1 year after it opened in 2014. So this is a year worth of data, say it like in August, September of 2014, after it opened in 2013. So as you can see here, originally the design Energy Star score was projected to be, it was actually a little lower than that, but Energy Star kind of changed some of the criteria. So currently, based on the current calculation of what the Energy Star score would be at design, it would have been, the design score would have been 96, and we were operating at a 72. So as you can see, not real glamorous results after the first year. But if you notice, there were still the energy savings that were there, which the owner was very appreciative of, and definitely like that. But there were some, we'll get into this in some of the evaluation of the actual O&M here shortly, but in a nutshell, these were variable speed compressors on the heat pumps. We had multiple compressors go out. There were some compressor issues on the DOAS units. So in that first year, there was a lot of equipment issues, staff coming up to speed on how the system worked, trying to get the system to work optimally. So there was a lot going on in that first year that obviously you can see the first year was not as good as everybody had hoped and we were planning. So this is after 2 to 3 years of operation. We actually hit the Energy Star score of 76. So it did take a year or two between staff training, getting bugs worked out of the system, et cetera, was able to hit the Energy Star score of 76. That energy costs per year continued to drop. It was around $610,000 per year on the energy cost side. And then this was actually August of 2017. You see that we were able to achieve an Energy Star score of 85. Again, and this is hats off to the facility staff that actually began to embrace the system and actually was working to optimize the system. And you can see this as the years of operation continue to progress. And so we would say it's very much, it's kind of like having a Cadillac for a real nice vehicle, but not being able to use it to its fullest. And so as the facility staff came on board, learned more about the ground source heat pump and started resolving issues and taking care of issues and optimizing, it really improved the results. So in July of 2018, actually reached an Energy Star score of 91, an EUI of 127.8. As you can see, the design goal for that was 120.2 in kBTUs per square foot for the site EUI. So as you can see, it continues to improve, as we moved into 2018 as well. And then when you get to, this is actually February of 2021, so a year ago this month, it was achieved an Energy Star score of 97 with a site EUI of 117.4, again with the goal of 120.2, and that energy cost was well below the design at 551, almost 552,000 for the year. And but it was actually when you compare that cost to the original 7-year analysis, it was even much more significant than that, close to about $140,000 less than what the original 7-year analysis predicted based on the life cycle cost and energy modeling, that kind of thing. Here's a graph. This is really the whole, well, I say that, it starts in January of 2016, but a graph of the electrical and gas usage. And as you can see, obviously the gas usage peaks in the winter in January typically. The electrical load pretty much changes, but it's actually reduced some as the years have gone on. And then obviously you can see in January of 21 there was a peak and a spike in the gas usage there. I'm not sure what that was about other than just colder weather, but even looks like that may have been somewhat of an anomaly. But anyway, that just gives you an overall view of the electric and gas usage for the project. So in summary, this is based on the July 2018 metrics summary, again, from and this is again based on 2018 data, but you see it with the base score, which in 2014, and again, that Energy Star score, the way it was evaluated changed over the years. So you'll see some differences between the original 2014 score we had and this 2014 score. But anyway, the point is, as the facility has gone on, that Energy Star score has improved, in this case by over 12%. The site EUI has continued to decrease, in this case by improved by over 14%, and the energy cost has continued to go down. This is a graphic representation of the latest data that we have, which was in February of 21. And again, note the increase in the Energy Star score of over 15%, and a decrease in the site EUI by over 20% from the baseline in 2014, and decreasing costs by over 17%. So we're very thankful, very excited, for these results, but a lot of it obviously has to do with a very energy efficient ground source heat pump system. And then one of the things that often does not get looked at, again, it gets overlooked in the selection of the project for the HVAC system, and then and certainly not as you go back and look at a project. In fact, when we first started putting all this data together, we were actually working on an article in the magazine we were working with, or the person we were working with writing the article, says, what about the O&M costs? You don't have any evaluation. So we went back and went to the facility and had them pull the actual operation and maintenance costs from 2014 to 2017. As you can see, that operational costs continued to decrease from 2014 to 2017. And we had actually, in our analysis, had projected close to $650,000 for the O&M costs. And we were right at that or below from, the whole time that the facility's been in operation. And then we talked some about, patient satisfaction earlier. So, part of the performance results were also tied to patient outcomes and satisfaction. So I won't go into all the details of this slide. This was actually a slide the facility put together for one of the presentations that they helped us with. But basically, Olive Branch ranks as the highest of any of their facilities within the Memphis area that's a part of the Methodist Olive Branch system. So again, from a patient satisfaction, so that has borne out. When you look at the hospital consumer assessment, the HCAHPS, patient satisfaction, again, it ranked 89th in the percentile nationwide with respect to inpatient care, 99th in ambulatory care, 95th in emergency care, 92nd in outpatient services. So I know that's a lot on that slide, so just summarize that for you. And then same thing on the HCAHPS. This is the survey of patient experiences. Olive Branch ranks ahead of both Mississippi and national averages on most HCAHPS scores. So obviously, Methodist Olive Branch is very pleased from a patient satisfaction arena as well. So from an operational side, we actually talked to the facility and said, hey, so what are the pros and the cons of this project? Kind of the the good, bad, the ugly, so to speak. But to hit the pros, which this is the first hospital in the U.S. to receive the LEED Gold for healthcare. Actually, I think we actually got it by minutes. There was another facility that was, I'm not sure which one it was or where, but there was one other facility going for the same thing. But we were actually just before. They were like the second, we were the first. But anyway, first hospital to get LEED Gold for healthcare. Obviously, cost savings over conventional HVAC systems, fewer full-time equivalent employees than conventional HVAC system in a hospital. This is actually done with one director and 4 O&M specialists, and no need for, as I mentioned earlier, that 24/7 boiler stationary engineer because we didn't have any boilers, no chillers, noise. The CEO of the facility, when he first walked in, was like he's never had a facility that was so quiet. So definitely there, and so anyway, and maintained overall, quality, which leads to better outcome for patients. So what were the drawbacks? Well, obviously I alluded to that earlier, but a learning curve for the staff because they were used to conventional HVAC systems. So a little bit of a learning curve on the geothermal systems, the way the piping, the system was set up. This actually came up early on when we went and looked at another, heat pump facility. But one of the comments the owner initially said, well, hey, that's when you have a distributed heat pump system, you don't have central air handlers, so you don't have all your filters in one place. So you got to go around and change filters. In this case, 215 heat pumps and 8 NOAS units. So that's a lot of filters to replace. But again, it's relatively straightforward, relatively. Not time consuming, and the fact that all of these units, that was one of the things after we went and looked at the project in Louisville, is they came back and the facility in Louisville actually had a few heat pumps that were ceiling mounted above the ceiling, and that's one of the things they said is, hey, put them all on the floor. So that's how we ended up with a small heat pump closets distributed around the facility, and they're all located on the floor. There were some. You oftentimes don't have a lot of leaks with geothermal bore fields, but this one particular did. It was partially located under the parking lot, not much of it. Thankfully, all the leaks were not under the parking lot, but there were some leaks early on that did have to be traced out and corrected. But once that was done, the pressure would be able to maintain on the bore field. And then just the fine tuning balance for the bore field, that's one of the things the facility, you know, kind of took upon themselves as far as the water balance to make sure that was done, that all the heat pumps were continuing to maintain their flow from the geothermal field. And as I mentioned earlier, we did have some frequent DOAS unit compressor failures, you know, primarily related to new technology, system effects, those kind of things that we did have to deal with on the project. Again, just some representative pictures. The slide on the left is the green sleeves pump skid as part of the predictive control. Already mentioned the closets. The one on the right is the water-to-water heat pump for the domestic water. So this kind of gives a representation. Again, this is just of the Methodist Olive, you know, facilities in the Memphis area. But as you can see, Olive Branch has the least of KBT per square foot consumption, and as you can see, it's significantly lower than a lot of their facilities. So again, the owner's very, very pleased with the energy consumption and obviously the reduced cost associated with that. One of the unique parts about this facility is it was not fully occupied. It was not fully, census was not at 100% early on. So this kind of gives you an idea of the patients served, and this only goes to 2016. But obviously, as the years have gone on, the number of patients has increased, but the energy consumption has actually gone down. So again, it's just a testament to the energy efficiency of the overall system. And again, I won't go into details on a lot of these, but again, this mainly kind of deals with some of the local facilities there in the Memphis area and how Olive Branch compares. But it is like a 4-star facility in the CMS awards, and it's really the only 4-star facility for Methodist Olive Branch in that area, and the same thing here. So anyway, it just goes to illustrate again the operational side of it. So we started out on the left there. That's a basic, you know, energy model. Can y'all hear me okay?
Yep.
Okay. I heard something.
Yeah, somebody's off of mute.
Gotcha. Okay. But anyway, you can see there the energy, you know, went from concept on the left to, you know, the rendering there that the architect did early on to represent it. And then as we further, you know, modeled the project, and then as you can see the progress of the construction and now a completed facility, which we're very excited to have. So,
don't worry, G.
but again, this summarizes that whole decision-making process that we covered for the A3. And then if you do want to, there is a HFM magazine that was in, I thought I had it up here. I think it's June of 2018. I thought I had that date up here, but I must have left it off the slide. But there is an HFM magazine article that actually covered this, the hospital's journey to LEED Gold, guided by the integrated project delivery. So
Thanks, Mike.
Yeah, we've got time for questions.
Yeah, we've got some questions on the chat line here. So great presentation, a lot of good feedback on that. Exciting facility you designed there, so that's fantastic. So a couple questions in the chat room. Was there a reason the hold depth was set to 300 foot? If, you know, space was a consideration, could it have gone deeper? What was your reasoning behind that depth?
Yeah. Well, and probably most of you know this, but the depth of the bore field is pretty much determined by the geological conditions. And we talked to drillers early on in the area, saying, hey, how deep could we go? And pretty much everybody came back and said, hey, probably 300 is about, and it's due to the clay sandy soil conditions there in the North Mississippi area. So yeah, the 300 foot was probably about a limit. Now, to give you a comparison, we have done a project in Lexington, Kentucky that was also geothermal heat pumps. It was not a hospital, it was ambulatory surgery and MOB, and it was smaller, but we were able to do the whole facility, including the DOAS units, on the bore field, and that, because it's limestone, we were able to get 500 feet deep on those bores. So you're right, but obviously the deeper you go, the higher capacity you have out of the bore field, but this was limited,
Right.
basically just due to the geological soil conditions. So.
Gotcha. Great. Another question was, did you end up finding out what source of the leaks were in the geofield? Were they improperly fused joints or something else?
You know, that's one of the things that I'm sure somebody knows exactly what happened. You know, the main thing is that they were corrected. I think we finally determined in talking with the installer, it may have been some of the resins that were used. I think there were some changes going on at that time with actually the resins in the pipe and actually what they used to join the pipes and seal the pipes. So we don't know for sure, but that seemed to be part of the issue. But the main thing is that they were able to be corrected and
Right.
it was able to continue to function. So.
Perfect. Great. Bill Nowak wants to know, was there any calculations done or data that translated the system into COP? Did you have any information on that?
No, I mean, I pretty much shared everything that we did. We probably could calculate that. We don't have that, you know, overall, but
Sure.
obviously it's done very well. So
yeah.
Yep.
John Chavaco asked if you could change one thing about the project design or equipment selection, anything you do differently?
Well, one of the things we'd like to have not had as many equipment issues on the front end. Although I'm glad we did it. I mean, a lot of the issues we ended up having was because the compressors, particularly in the heat pump, were variable speed compressors. So, I mean, I guess one of the things we saw was, you know, when you go with new technology, you always kind of open yourself up to potential, you know, operational issues, and I think that was the case here. So, I guess if we had our druthers, we would rather use more proven technology, but in this case, I don't know that we would have moved away from it, just simply because the variable speed compressor was such a big plus. You know, once the bugs were finally worked out. So.
Great, and that kind of tied into another question that somebody asked. Why do you think that, you know, you mentioned you had some issues up front? You know, what was that related to? Is it more of a manufacturers or installation or design, or so it sounds like maybe it was just newer technology.
It was newer technology, and as I mentioned, we had compressor issues both on the heat pumps and the DOAS units. The DOAS units actually ended up being longer lasting, but again, I would just say mainly those were probably more equipment related. There was a few things that maybe we kind of stumbled on from a design perspective that we tweaked on the DOAS units, as far as we were using VAV boxes to actually control the amount of outside air for a group of boxes. And so there were some control adjustments that in the process of looking at everything, that we made some adjustments there. So there were, I would say there was a few design related changes that we had some lessons learned as well. But as far as the equipment operating, it seemed to be, you know, primarily, you know, equipment related.
Yeah, and I think as you and I both know, on this, being in the engineering side, the control sequence and getting the controls contractor to get it programmed exactly how you kind of specify the sequence can be challenging. So that's always a lot of tweaking after system startup.
Right.
Another question here was, were your operating rooms also served with local ground source heat pumps? Did that pose any issues with pressurization requirements?
They were, and I failed to mention that earlier, but we did. I believe they were 6-ton heat pump units, and they were roof mounted because, again, we didn't really have any mechanical room, so they were roof mounted. The ORs were on the second floor, so they had roof above them. And then what we did, they actually wanted a little bit lower temperatures in their ORs, not quite what we would consider, you know, full low temp, but they did want lower temp. So we did a active desiccant dedicated outside air unit to the OR heat pumps. So we did the whole facility. The final units on any area of the facility were heat pumps. We did that in the ORs as well.
Great, thank you.
I take that back. I think we did have one. We had one or two crack units. I think they were DX for some MRI equipment, but majority of the whole building was, like I said, over 215 ground source heat pumps. So.
Great. And I think last question here, and I think we're just about ready to wrap up. John, want to know about the compressors that had failed. Do you think maybe it was a too much low speed operation? Anything of that nature? Or was it just something else?
I mean, it seemed that, I remember early, and again, it's been several years ago, one of the things I remember coming up was there were some harmonic issues that it seemed to be when the speed of the compressors changed and they reached a certain, frequency, there was some vibration. And so one of the things they actually did on some of those compressors was actually kind of bypass that particular speed when the compressors ramped up and down. So from what I recall, that was, at least on the heat pumps themselves, it was a harmonics vibration issue that caused a lot of issues.
Gotcha. Great. And another question that came in from Xiaobing is, were the DOAS units also connected to the ground loop, or were they just wheels and conventional?
Right. They were not connected to the geothermal bore field. Again, mainly we could not expand that field any larger, so we put the outside air unit as purely DX and energy recovery is what we did on the DOAS. And we had there were 8, I believe it's 8 DOAS units that served the entire facility. So.
Right. All right. I think we'll take this one last question. It's a pretty simple one here. It says, were you able to use excess heat from one area to heat another area, which was, so basically simultaneous mode. And obviously with connected heat pumps, that is the case if needed. So if one was in heating, one was in cooling, you certainly move heat around. So yeah, fantastic.
Yes, definitely. And
well, great.
Yep.
Great job.
And minimize the reheat. So, great.
Yeah.
Thank you.
Yeah, perfect.
Appreciate
Great job. Thank you. Yep, we appreciate your time and presenting. It was a great project, and thanks everybody for joining. Hope to see you again at the next town hall. Have a great day.
Thank you.